Hello students, welcome back to PH107 Quantum Physics and Applications. Today I am going to discuss Fourier transform and Heisenberg uncertainty relation. So let's recap first what we have learned so far. So in the previous lecture we have seen that if you have any periodic function of period L, which is f of x, so let's f of x is a periodic function with period 2L, then this function can be expressed in terms of the sinusoidal functions, and this expression is known as Fourier series. Okay, and when we move from a periodic to the non-periodic function, this summation changes to the integral, and in this case also any non-periodic function can be written in terms of the cosine and sine in this following manner. Okay, and this gives a new relation that we have f of x. This f of x is related to the g of k, where the g of k is written in terms of the ak and bk. So this f of x is related to g of k by this integral, and now this integral is known as a Fourier transform, or you could do a revert this relation. So you could say that g of k is written as in terms of the integral of f of x with respect to the power minus ikx dx, and 1 over square root of 2 pi is the normalization constant. Okay, so this is the first thing that we have learned, and to just use this expression we have picked a particular example. So in this particular example we have defined g of k is 1 in this particular range of k, and then 0 otherwise. So if you plot this function g of k, it looks like something. So it is 1 in the range of k0 minus delta k by 2 to k0 plus delta k by 2. Okay, and now if you put this value of g of k here and take the appropriate integration limits, then what you have seen that you have written the real of f of x is in this following fashion. And if you want to plot this function real of f of x, it looks something like that, where this blue curve or the oscillations are your cosine of k0x, and this broad envelope is your delta k divided by square root of 2 pi times this sine function. Okay, now what we have done before we closed our previous lecture, that let's increase the value of delta k. So here we have increased the value of delta k in this following fashion. So you see that this dotted line is the increased value, and see how this is going to affect this relation. So first of all, note down that the extent of this wave packet, which is ranging from minus 2 pi over delta k to plus 2 pi over delta k, so the spatial extent is 4 pi divided by delta k. So now you know that if you have increased the value of delta k, it means that the spatial extent will shrink, and that's what we have seen. So this was the things, and as you increase delta k, then your delta spatial extent will shrink, and along this vertical direction it will increase. So it means that the delta k or the k and the x, or delta k and delta x spatial extents are not independent with each other. They are related by some constraint, and this is what we are going to discuss in today's lecture, and what is the consequence of this constraint. Okay, so the spatial extent of the function real of f of x, that is delta x, decreases as delta k increases, and this is what is known as a reciprocity relation. Okay, so in other words, both delta k and delta x cannot become arbitrarily small. As one decreases, the other increases. And in the case of function that we have just constructed, where we have seen delta k and delta x, and we know what is the value of your delta x is 4 pi divided by delta k. So this product of these two variables comes out to be 4 pi. In general, for all wave packets, the following relation holds true. So delta k, delta x is approximately 1. Okay, so far we have only seen, or we have only considered functions in space. Whether you could say that we have considered the function in terms of x or in terms of k. What about if we want to expand this concept, and instead of going into the k x space to some other space, for example frequency space or time space, what will happen? So let's consider a function which is localized in time or time pulses. So these are what we can call as a time pulse. Okay, so this is your time and this is your amplitude, and these are what you say the square wave. Okay, and in that case also, by using the same uh, concept, we can simplified or straightforward way, we can extend this concept that if you have a function g which is a function of frequency omega, then by performing this Fourier transform, we can get a function in time domain, or vice versa. If you have a function in time domain, we can perform a Fourier transform and we can get a function in frequency domain. Okay, so now we can also use this concept of the reciprocity relation, and we can say that delta omega, the small increment in time, we will see what is the real meaning of delta in coming time. Okay, so delta t and delta omega, the product of the two is always approximately 1. Okay, so let's do some more examples of this Fourier transform or Fourier integral. So let's say first we have a function f of t is alpha, which is a constant, it does not depend on any variable t or omega, and let's estimate what is your g of omega. So here is a simplified definition. So if you substitute this alpha here, because alpha is not dependent on t, so you can take out this alpha outside this integral. So now you have left with the integral going from minus infinity to plus infinity e to the power minus I omega t dt, and the value of this integral is your delta function, which is a delta of omega. This is a definition of your delta function. Okay, it's not coming out from a rigorous way, but this is how the delta function is defined. Okay, so if you want to extend this concept, so here is the idea. So let's say if you have an integral e to the power minus I omega minus omega n, so now your frequency you could think of shifted by omega n times t dt. This will give you delta of omega minus omega. So whatever you have the multiplication with t, this will go as the argument of this delta function, and if you have only omega, then it will go to the delta of omega. This is what we have written. So what it means that, let's say in temporal domain or in time domain, your function is present everywhere because it is not dependent on time. So whatever value of t you choose, the value is always alpha. So this is extended in time domain, and if you go to the omega domain or frequency domain, it means that the function is very well localized at omega is equal to 0. This is the definition of this. So this is how the delta of omega in omega domain looks like. So this is a p. Okay, so g of omega is 0 everywhere except at omega is equal to 0. Okay, now we can extend this concept, and let's say we can use an oscillatory function like cosine omega 0 t, where omega 0 is a frequency of this function. And now we know that this cosine can be written as in terms of the exponentials. This is what we have seen in the previous lecture when we wanted to convert our periodic function to the aperiodic function. So this we have written cosine. Okay, and here is your definition of g of omega. So here you have e to the power I omega t. So now you can collect the first term and then the second term. So this is the first term you get, e to the power minus I omega minus omega 0 times t, and this is the second term. And by using the definition of delta function which you have seen in the previous slide, you can easily write down this is your delta of omega minus omega naught, and this is your delta of omega plus omega naught. So what it means that if you see or if you look in a graphical way this function g of omega in frequency domain, it means that the function is peaked or non-zero at value minus omega naught and plus omega naught and 0 elsewhere. Okay. Now you could do the same exercise for sine omega t and get what is the value of your g of omega. So this is an exercise that you have to do and submit the answer. So, and this is the definition of your sine of omega t. Okay. So the concept or the relation that we have just obtained in between the t and omega, or let's say the time domain and frequency domain, using the Fourier relationship. This is a very, very useful relation that you are going to learn in coming classes during your BTech study. For example, this is a very important application that you use in signal processing. You use to find different frequencies of any system. What are the frequency components involved in any signal by just performing the Fourier transform. Okay. So now let's come to another very interesting function, and this is a function that is going to be present throughout your quantum physics, or if I want to say this function is going to be present throughout your physics course, not only limited to your first year BTech, but during your entire study. So a function which has this particular form is called as a Gaussian function. So what it has? So it has exponential minus x minus a square divided by sigma square, and then this function has this normalization constant. Okay, and if this is a function which is known as a Gaussian function, okay, or Gaussian distribution, if you plot this function looks like this. So this is your x-axis. So this x minus whatever quantity you have is the position at which the function is peaked. So this function is peaked at value x is equal to a, and you could see what is the meaning of this sigma. We will come in a next lecture that what is the real meaning of this sigma, or maybe at the end of today's lecture. If you look, the value of this function 1 over e times the value of this function at both ends, then you will see that the value of this function 1e of this function is situated at a plus sigma and a minus sigma. What is the meaning of this? The meaning of this that the size of this function, let's say you could say this distance delta x is sigma. Now I'm coming to the definition of delta x that you were using. So delta x, I could say is sigma. It means that your 99.93% of the wave packet is limited in this range of a plus minus 3 sigma. So this is the range that you have said that this is the range at which your most of the wave packet is localized. Okay. So now I can do again a Fourier transform and try to learn some more properties of this Gaussian function. So here is your f of x. Here is your Fourier transform e to the power minus I kx dx. And if you perform the Fourier transform of a Gaussian function, it's a Gaussian function. And that's why this function is a very important function in physics, or in general in science and engineering, because the Fourier transform of a Gaussian function is a Gaussian function. Addition of a two Gaussian function is a Gaussian function. Product of a two Gaussian function is a Gaussian function. Division of a two Gaussian function is a Gaussian function. So Gaussian function remains Gaussian. Okay. So here is a Fourier transform of this Gaussian function. So now let's estimate what is the delta k and delta x. Okay, and then we will demonstrate that the product of these two variables attains the minimum value. So the Gaussian function is the only function which gives the minimum value of this quantity, or this quantity. Okay, so which is delta k, delta x come out to be half. Okay, so now we can use from the reciprocity relation and say that the product, or we could put an upper bound of the value of this product, that this product cannot be smaller than half, because the smallest value, which is half, is only possible for the Gaussian function. So for any other function, the product must be larger than or equal to half. So this is the general reciprocity relation for delta k, delta x. And now we have to try to understand the meaning of delta k and delta x. And now we have to go from functions to the distribution function. So let's say if the function we consider so far is the distribution function. Okay, so think about psi of x or f of x as a histogram in x, with a representing the mean value and sigma represent the standard deviation. So I hope that you know the meanings of standard deviation and the mean value of a distribution function. Then we can say that a is the mean value of x and sigma is the uncertainty in the value of x. Okay, so this is how we are trying to relate, or this is the how the sigma is related to the uncertainty of finding the value of x, where x has the mean value a. Okay, so then we could say that if we want to know the value of x, which has the mean value a and uncertainty sigma, then we could say that the value of x in general can be written as a plus minus standard deviation sigma. Okay. If psi of x is now considered as a wave packet instead of a distribution function associated with a particle, then a would be the mean position of the particle and sigma would be the uncertainty in determining the position. So let's recall, this is what we have learned from the reciprocity relation, and if we use these two concepts, then we could easily say that the Driboi hypothesis allows us to associate the momentum of a particle p to the wave number of the associated wave packet. This is the relation that we have seen, p is equal to h cross k. So this is what we have seen from the reciprocity relation. We have also seen the p is written as h cross k. So now this relation I can write down in terms of delta p. So this comes out. So delta p times delta x, where this p has a momentum. Momentum is a vector. So here you could think of this is the x component of the momentum. So delta px, delta x is greater than or equal to h cross by 2. The same concept or the same thing we can employ to our delta t delta omega. And this is what is known as a Heisenberg uncertainty principle. So this is what we have seen a reciprocity relation in time frequency domain. And if you use your omega is your h cross, if you use E energy is equal to h cross omega, then we can easily write down delta E is equal to so if you use E is equal to h cross omega, then we can easily replace this delta omega by delta E and the h cross comes here. So this is energy time uncertainty relation given by the Heisenberg, and this is the momentum position uncertainty relation given by the Heisenberg. Okay. So this is another way to understand this delta x, delta p uncertainty relation. So let's say this is your wave. Here I have plotted sine of 5x. So an ideal wave has precise wavelength. So here the wavelength is related with this 5. So it has a fixed wavelength. Therefore k is precisely known. So k is your 5. This implies that the wave extends from plus infinity to minus infinity, which means that the position is uncertain. Okay. So if your k is very well known, it means that the position is very ill known or ill defined. Okay. Now if you add many waves, here we have seen that we have added 17 waves. Okay. It means that now what we have done, we have added large range of wavelengths, means their k is becomes more uncertain. So we don't know what is the value of k. K could be 5, 5.06, 5.12, 6, 5.9, anything. So there is some uncertainty in your k value now. But the position of your is certain because your wave is localized into this vicinity. So it means that if you are trying to know the value of wavelength or the wave vector in a precise way, then your position becomes uncertain and vice versa. Okay, so the delta x is the uncertainty in position. So in this case your delta x is very uncertain but your k is certain. Now in this case your delta x is very certain but your delta k is very uncertain. So delta x delta k remains always as 1, and if you want to convert this delta k into delta p, then it will be your h cross. Okay, so what we have learned so far is smaller is the spatial extent delta k. It means that the larger is the range of your wave number delta k, okay, which need to be used to form a wave packet. Similarly, we can say that if the time domain delta t is small, it means that we require a wide spread of frequency to form a group. So this is the same logic we can apply to the time frequency uncertainty. Okay. So now let's try to understand some more meaning of this position momentum uncertainty. So this uncertainty or this upper bound sets the intrinsic lowest possible limit on the uncertainty in the knowing the value of your px and x, no matter how good an experiment is made. So this uncertainty is not related to the resolution are the quality of the instrument which is going to measure the position or the momentum of the particle. So these uncertainties are inherent in the physical world and have nothing to do with the skill of the observer or the experimental conditions or the quality of the instrument and so on. Okay, so it means that it is impossible to specify simultaneously and with infinite precision the linear momentum and the corresponding position of the particle. The same we can say about energy time uncertainty. So let's say if a system is known to exist in a state of energy E over a limited period of time delta t, it means that this energy is uncertain by an amount h divided by 4 pi times delta t. Okay, so this is clear from here that the uncertainty in energy is h cross divided by 2 times delta t, and now h cross is written as h over 2 pi, so that's why it is h over 4 pi times delta t. It means that the energy of an object or system can be measured with infinite precision only if the object of the system exists for an infinite time. Okay, if delta t goes to infinity, it means that your delta t becomes 0. It means that if you want to measure the energy of the system, it becomes precise with over the time. So with infinite precision if delta t goes to infinity. So this is what we have seen energy position momentum uncertainty relation. This is what we have seen energy time uncertainty relation. So now you could ask why certain variables come into pair. What is the reason behind it? Okay, so the concept that we can say or we can build up is that there is something called conjugate variables. So what are the conjugate variables? Those variables. Now this is a definition. Those variables which satisfy these uncertainty relations are known as conjugate variables. So for example, x, px, et are known as conjugate variable. So now here I have written only one component of your momentum position uncertainty. Now you can write another component, and another components are also conjugate variable. Okay, now if you want to mix up some variable, for example xpy or ypx, they are not the conjugate variable, so they will not fulfill the uncertainty relation. Okay, now these conjugate variables cannot be measured or known to infinite precision simultaneously. So here is a general uncertainty relation or complete set of uncertainty relation I have written. So here is another question for you to answer. Other than these 4 set of uncertainty relation, can you come up with another set of uncertainty relation or another pair of conjugate variables which fulfills the uncertainty relation? So this is the answer that you need, this is the question that you need to answer. Okay, so this is what I have said, that let's say if you have any measurement to determine px does not introduce any uncertainty in y or z and so on, because y and px are not conjugate variable, z and px are also not conjugate variable. Okay, so let's do some application and try to see how the uncertainty principle or the uncertainty relation is very useful in quantum physics, and what are its applications and what are the insights it can provide about the physics. So first question we want to ask, can an electron 2 be found in the nucleus? Okay, I hope you know the answer, but let's try to understand this question in the language of uncertainty principle. Okay, so let's say the size of your nuclei is 10 to the power minus 14 meter. This is what I have said in the previous lectures, and this is your Fermi dimension, nuclear dimension. Okay, and let's say this is the size, so this is like a diameter, so we could say what is the radius, and let's say assign this is the uncertainty in delta x, so delta x will be 0.5 times 10 to the power minus 14 meter. Okay, now I could easily compute my delta p. So delta p is h cross over 2 times delta x. I know the value of all these things, so this comes out to be 2 into 10 to the power 7 electron volt per c, where c is the speed of this one. Okay, now I can calculate my total energy using this expression which we have seen earlier. So once you substitute this expression, and calculate everything, it comes out to be something around 20 mega electron volt whole square. Okay, and this is enormous energy. Okay, so E comes out to be 20 mega electron volt. Okay, you know what is the energy of an electron, for example, in hydrogen atom? These energies are of the order of some eV. I mean, you cannot define precise energy of an electron, but you can define the energy of your energy levels, okay, which are few EVs. Okay, so this energy, which is much higher than these energies, okay, is nowhere. Or if you want to calculate the kinetic energy, so the kinetic energy, you know, is this energy minus mc square by using this expression. Okay, so or you could say, sorry, you could say that the kinetic energy is written as the total energy minus rest mass energy. We know the rest mass energy of an electron is 0.511 MeV, so this comes out to be 19.5 MeV. Okay, and this is too large. It means that electron cannot reside inside the nucleus. Okay, because this contradicts, or what I said, that this energy is much larger than the energy of your energy levels in hydrogen atoms, which are few eV. Okay. Now another very important concept that comes from uncertainty principle is about harmonic oscillator. Okay, so let's recall Planck's radiation formula, which requires the oscillator energy to be quantized. So the total energy is written as n times h nu or hf. Here I have used f for the frequency, okay, where n is an integer quantity. And later on you will learn in some other courses that it required some additional correction, and this is known as half hf, and this is called a 0 point energy. So the correct total energy of your harmonic oscillator is n plus half hf, and this half hf is 0 point energy. Okay, so that's what I said, that if n is equal to 0, if you do not have any value of n, it means that still you have energy of your harmonic oscillator, and this is the lowest possible energy of the oscillator is half hf. Okay, this contradicts your classical notion, because if there is no value of n, then how it could be that you have some energy associated with the system? So the lowest possible energy according to the classical theory is 0 when the oscillator is at rest. Okay, but quantum mechanics allows you to give this in, and this is a very famous 0 point energy of harmonic oscillator, and it has a very wide applications. I will name few after finishing this exercise. So let's say how this is related to your uncertainty principle. Okay, so 0 energy implies both position and momentum of the oscillators are 0 with certainty, which contradicts, because we both cannot know with certainty that position and momentum with the value of position and momentum with certainty. Okay, so what we can do, that let's write down first total energy of your harmonic oscillator and then takes its average. So the total energy of your harmonic oscillator is half m omega square x square plus p square over 2m. Now because I'm going to take the average of this energy E, so I have to take the average of my x square and average of p square. Okay, now when your harmonic oscillator is in equilibrium or at rest, it means that the mean displacement or the average value of the displacement x and the average value of your momentum p is 0. Okay, this is one thing. And now I can write down this x square using the definition of standard deviation in this following fashion, which you know, the same I have applied it here. As I said that the average value of your displacement and average value of your momentum is 0, so this equation average value can be written as this one. Now I can use the uncertainty relation between delta p and delta x, and then I try to combine and get one relation. So this is the definition of my delta px in terms of delta x. So my total energy can be written as in this following form, and now I can minimize this energy with respect to delta x, and once I minimize the value, I will get that it comes out to be half hf. So you have seen now that the 0 point energy of a harmonic oscillator comes from the uncertainty relation, or can be achieved by the uncertainty relation. And as I said that this 0 point energy has a very important consequence in physics. One of the important things you may learn later, or you could learn by yourself, is related to the vacuum fluctuation or Casimir force, which have a lot of technological applications. Okay, here is another application of uncertainty relation. So let's ask, what is the size of an atom? Okay, so let's say an electron be confined in a spherical cell of radius a. So let's say this is the uncertainty in delta x. Now this is the uncertainty in delta p. Okay, so the total momentum can be written as a p plus minus uncertainty. But we know from our previous example that the initial or average p is 0 when system is in equilibrium. So now your delta p total is approximated as only delta p, and delta p is your h by a. Now this is again total energy is kinetic energy plus potential energy. So this is my kinetic energy, this is my potential energy. An electron in hydrogen atom, for example, and a spherical cell of radius a, potential energy I can write down. This is the potential energy you have learned in your electrostatic. Okay, kinetic energy I have written p value here, so this comes out to be this one. Okay, so now your energy E is related to this variable a, rest of them are constant. So now you can take optimize this thing, delta E over delta A is equal to 0. This will give you the value of a, and if you substitute all these values, then you will get this E minimum, which comes out to be correct. Okay, now this is a last example, and this example is going to use time frequency uncertainty, and this I'm going to tell you that how this is very important. So let's say this is your hydrogen atom. You by some means you have excited an electron to n is equal to 2 level, and at some point of time this electron will come back to the ground state and will emit a radiation h nu. Okay, so because this is your ground level, so this has lifetime infinite, and this is your excited level, so it has a finite lifetime, and this lifetime is 0.625 nanosecond. You know what is the photon energy between these two levels? So this is the Rydberg formula I'm going to use. So this is your 13.6. 1 over n1 squared minus 1 over n2 squared. So if you substitute all these values, the energy difference between the two levels comes out to be 10.2 eV. So here you see that your energy levels is of the order of eV, whereas the total energy comes out to be milli-electron volt when you have seen in the previous example, if your electron is supposed to reside inside the nucleus. So this contradicts, it means that your electron cannot reside inside the nucleus. So let's come back to this problem. So here is the energy difference. So now here is your delta T, and this delta T is related to the lifetime of your excited level. So the uncertainty in the energy due to the finite lifetime is comes up to be this value. Okay, and just to make a side remark, only knowing the uncertainty in energy or uncertainty in time or the lifetime has played a very important role in developing quantum technology. So for example, the concept based on the laser cooling, or your current quantum computer based on your qubits utilizes all these concepts. So this is the how the technology or the concept has been developed and employed to the current technologies. Okay, so now you can estimate delta E. So before I end, let me make a comparison where and how the uncertainty relation is going to play in your living world, which has two distinct quantities which you could call as a macroscopic object and microscopic object. So let's take an example of microscopic object. A cricket ball has mass 100 gram, velocity 40 meter per second. So you can compute momentum. Now you say that momentum is measured to an accuracy of 1%. So delta P will be 1% of this one. So this is comes out to be 4 into 10 to the power minus 2 with SI unit. And now you can calculate the uncertainty in the position. If the uncertainty in the momentum is 1%, so the uncertainty in the position of the cricket ball comes out to be 10 to the power minus 33 meter. Now if you go to the microscopic world and take an electron and you say that the same is true, then the uncertainty in the position comes out to be 10 to the power minus 4 meter. So comparing the size of an electron, which is of the order of angstrom, okay, or size of the orbit roughly, we will come what is the correct word, but at this point you can consider as size of an electron or size of a Bohr orbit is of the order of angstrom. So the uncertainty is much larger than the size, whereas here the uncertainty is much way smaller than the size or the mass of the electron. Okay, this is the same what you have seen in the case of Debye wavelength. Okay, the Debye wavelength for a macroscopic object comes out to be the same order, but the Debye wavelength of a microscopic object comes out to be of the order of 10 to the power minus 10 meter. That's why the uncertainty relations as well as the wave particle dualities and all are related with each other are going to play an important role and very crucial role in our microscopic world, which are one way or another way is going to use or used to build the technologies. Okay, so before I end today's lecture, let me provide the recommended readings. Okay, so if you would like to read more about Heisenberg uncertainty principle, please go to section 5.5 in this book. And if you want to read additional information about the Fourier transform, you just follow this book by Irvin Krejcik, Advanced Engineering Mathematics. Go to chapter 10, which has a very nice introduction about the Fourier transform and all the useful mathematical identities. With that, let me thank you very much and see you in the next class.